as all structural weight is carried by the buoyant lift of the helium. Further, as only 50% of the sling load is lifted by the rotating fixed-wing aircraft, the Cyclo Crane is highly cost-effective by virtue of the sharply reduced power requirements vis-a-vis the helicopter. The rotational velocity of the airfoils in hover is established as equal to the forward speed of the Cyclo Crane in non-rotating forward flight. Thus, the upper and lower wings automatically provide the same lift in hover or in forward flight. The fact that all structural weight is supported by the highly cost-effective buoyant lift of the helium allows the Cyclo Crane to use low-cost, long-life systems, as heavy components are a normal part of the Cyclo Crane design. The Cyclo Crane was built in these areas after the lower engine has been started and allowed to come to operating temperature. The airfoils are realigned to the hover position and rotation begun. The vehicle will be allowed to reach a rotational velocity that will result in the generation of centrifugal forces on the engines of 1G prior to starting the second engine. Auxiliary hydraulic power is used to supply airfoil positioning on the unpowered systems before the second engine is started. This allows the pilot to control the vehicle under single-engine operation. Notice the stable condition of the vehicle under these conditions of single-engine operation. The pilot is easily capable of maintaining the sling load in the desired position, and the safety of the vehicle is never in question. The second engine is now started, and after warm-up, full power is applied. This first sling load was a 1,000-pound logging chain. Controllability was excellent, and all systems functioned as expected. A four-man crew was on board: pilot, flight engineer, co-flight engineer, and computer operator functioning as data recorder. The cab environment was pleasant. No vibrations or accelerations were encountered. The noise level was low, and a normal voice was more than adequate for communication. No previous lighter-than-air vehicle has ever been able to perform this maneuver. A lateral wing cyclic command from the pilot results in a thrust vector for direct lateral movement. This force could be used to counter a side force produced by a wind gust. Collective commands on the blade airfoils, directly analogous to a controllable pitch propeller, results in substantial forward movement even without realignment of the wing airfoils. This thrust vector can be used to maintain a ground position when the Cyclo Crane is accepting or releasing a load under wind conditions. When loaded, any loss of power results in a gentle descent until the sling load touches the ground. The vehicle then resembles a well-anchored balloon. In this test, the engines were turned off, and the ground crew had no difficulty whatsoever in securing the handling lines. In operation, the Cyclo Crane would now be pulled down, the crew would leave the cab, and the vehicle allowed to rise to a safe single-line mooring altitude.